Hi, my name is David, and I'm going to be talking about Infra Cloud Service Platform, or ICSP for short. And we're excited to tell you about this as it's Meta's way of rethinking how to operate and develop services in our infrastructure. In my talk, I'm first going to tell you about the problem statement motivating ICSP, go over the high-level design, do a couple deep dives as examples, and then take a look forward. Before I talk about ICSP specifically, I first want to discuss Infra Cloud, which is Meta's effort to move towards a private cloud setup for using infrastructure as product developers. We'd really like to remove the complexity of interacting with infrastructure at scale, but there's many challenges to get there. We know that there will be more developers at Meta, the number of services that they're building are increasing, and the physical data center footprint in order to support our workloads is going to continue to scale as well. We don't want to expose product developers to all these complexities. And so the goal of Infra Cloud is to hide this complexity from our product developers and let them focus on building new applications and products. ICSP within this focuses on the server development and operation. To give a little bit of historical context about services at Meta, we have to rewind the clock quite a bit and think about when Meta was primarily running the Facebook site. At that time, we had a very high-scale, high-reliability system, but our architecture was relatively streamlined in terms of services. We had things like web servers, caching layers, and databases. As Meta has expanded into new and interesting products like Instagram, WhatsApp, messaging, the backend services needed to support these types of applications have grown in both complexity and number. So now, if you look at our backend architecture, we have lots of really interesting and complex service workloads like video processing, search, or AI. And this is very exciting, but anyone who's run a large-scale service knows that this is a complicated task. So what problem is ICSP trying to solve? Our goal is to reduce the complexity of building and operating services at Meta. You can think of this a little bit like a general purpose platform that we're providing for service owners to use the service management capabilities that they need to operate a service properly. And so it's a little bit like a platform as a service offering, but the breadth and complexity of applications we need to support is generally broader. We also need this to be extensible as we have an eye towards AI applications that are up and coming, and we want to make sure that this platform supports these as well. I want to give you just a taste of why the current development workflow for service owners is complicated. And this is a bit of a simplified example, but it will give you a sense of why we need to improve this. As a service owner, you need to interact with multiple capabilities, and we call these domains, like routing, deployment, and push are all things that you need to have a properly running large-scale service. For a service owner today, they often need to interact with different systems that provide these capabilities, and this is a simplified example. So if I go set up my service, I may have to go to System A for routing, and I use a CLI to configure a database. I then go to System B for deployment, and I need to write a script to launch different jobs, which will give me the containers that my service is running. And then I need to go to a third system, System C, and perhaps this has JSON, which describes how my push works. As you can see, the interfaces and workflows for the user are all different here, and they also generally have different semantics and expectations about how they work. This leads to what the customer experience for building a service looks like today, where the service owner has a mental model of what they want their service to do, but they need to go and assemble the pieces themselves. Often customers need to have their own scripts, which then translate what they want to happen down to the underlying systems themselves. And this is not ideal because we have inconsistent APIs for them to work with. They end up having kind of opaque workflows that aren't clear how they're going to work, unclear semantics, and no single model for how to orchestrate the system. Hence, we're introducing ICSP, which is a single platform layer that service owners can use to define and manage their service. This is a high-level view of ICSP where users can come and use our UIs, CLIs, and APIs in order to set up and manage their service through what's called the control plane, which we'll discuss later. Hopefully, in our future world, we have a much better state where the user can reason about the value that this is providing them in three fundamental ways. The first is the control plane, which is a single place to configure and manage the entire service from the user's perspective. The second is we introduce the service data model, which is a logical description of what they want their service to do that all the different capabilities can bind to and understand. And the third is exposing platform APIs, which allows us to build new applications on top of this platform, like AI platforms. The scope of ICSP is quite large, and we're both excited and looking forward to how we're going to get all these services at Meta onto this platform over the next 3 to 5 years. However, because this is so ambitious, we need to bake in some key requirements into this platform to make this feasible. The first is that ICSP is modular. This means that we can bring systems onto ICSP in domain steps so that you don't have to move an entire large-scale service on all at once. The second is that it's extensible. This means that we can adapt or add new capabilities to the system to support future workloads that perhaps we're yet to learn the requirements of. Next, I want to tell you about the high-level design to meet the problems and requirements we just went over. Before we get into the design itself, though, I'd like to talk about some of the guiding principles for ICSP and how we reasoned about this. There's 4 I'd like to cover. The first is it's a unified product. And what this means is that you can configure, manage, and observe the service all in one place through the platform. The second is it's a declarative system. What this means is that the user asks the platform what they'd like to have happen without specifying how it actually happens. And this allows the user to delegate to the system how to enact the subsystems and domains on their behalf. The third is that we focus on APIs, the data model, and documentation. This way, when service owners or developers building platforms interact with the platform, there's clear contracts and behaviors that they can expect from the underlying platform. And fourth, it's a polyglot system, meaning that we can support different kinds of implementation languages for the actual service code itself. At a bird's eye view, you can think of ICSP the following way. Developers come to Infra Cloud to access different products inside infrastructure that they need to build out new and exciting products. ICSP is a product that they use if they need to run a backend service at scale. Within ICSP, there's 2 major categories of functionality. We have a service code experience, which is how you author the logic inside your service that you want to deploy. And the second is the management interfaces and capabilities, like routing, deployment, autoscaling, and so on. In my talk, I'm going to focus on the management interface and how we've designed that. The first really important concept to understand is called the control plane and controllers. So as we mentioned, a user comes to ICSP and they interact with our UIs or CLIs to configure the platform to manage their service on their behalf. And this happens through a central layer we call the control plane, which you can roughly think of as a database that takes in the user's configuration intent. There's also a concept called controllers, and controllers are implemented for each of these different domains like routing, deployment, and autoscaling. Controllers can also read from the same control plane and actuate the underlying systems according to the specification. But they also do more in an important way. Controllers also write back state to the control plane, which makes it explicit to the user when they want to introspect what the underlying capabilities are doing. We also use the control plane as a coordination mechanism between domains. And this allows us to use composition as a tool between domains in a centralized way that is both uniform in behavior and observable. I want to highlight one of the unique aspects of how we're designing this. We have a concept called the domain API. And this is a contract that every domain inside the system implements. And we can expect certain kinds of inputs and outputs through this API and certain kinds of behaviors. Specifically, the domain API specifies how configuration is received by a domain, its interpretation of topology, which we'll talk about in a moment when I talk about the service data model, reporting state back into the control plane, and the inputs and outputs between domains as explicit objects in the system. By specifying this API for domains, we create a lot of nice properties now that we can have consistently across these. One is that these are modular. Because the inputs and outputs are explicit, as we add these in piecewise into the system, if we need to bind their inputs and outputs to other systems, we can. The second is that we can expect uniform behavior, both in how they accept configuration, how they report state back, and how they understand things like the service topology. I also want to touch on another unique part of the design that we call facets. One of the really nice parts about ICSP is that we're building it to support different kind of actors that want to interact with the system. So service owners are humans that are coming and landing config changes themselves. And we also want to support platforms that are built upon ICSP, and we'll use what we call platform or automation pathways. And while this is a really nice property, we do need to guard against some behaviors, like what if a human and an automation tell the system to do the same thing? Well, we protect against this with what's called facets, which are unique storage locations for each actor. There's a human, an automation, and an emergency location that configuration is written into in unique locations. This provides an explicit lineage of who did what in the system. And so if we need to figure out, hey, there's an emergency and the human config needs to take precedence, we can clearly see the difference and then have resolution logic on top of that. Another big concept I want to introduce is the service data model. And this is a logical representation of the service from the service owner to the system. In many cases, service owners need to break their service into logical pieces. For example, they may have a production side of their service and a release candidate where new binaries are tested. We often call these RC. Typically, the configuration settings for production in RC may not be the same for capabilities like routing or deployment. What having a single logical model allows is that the user can specify different deployment groups for each of these specializations within their service. And there is a singular hierarchy that you can use when setting your config settings for routing, deployment, or push that all of them natively understand. So when you set your routing settings and your push settings, they both understand what RC means based on this logical model. The service data model becomes even more powerful when we talk about advanced concepts like multi-tenancy. Multi-tenancy exists whenever a platform owner has multiple customers and they want to have separate instances at a logical level within their platform to provide the capabilities back to those customers. I think this is most easily understood with a concrete example. So imagine you're running an async processing platform where you take jobs into the platform, it's put in a queue, and then you have workers perform work. Customers that come in may need separate logical footprints that we call tenants. And these are subdivisions of this overall platform. As you can see, here we have different services that compose the platform, like the queue service, the dispatcher service, and the worker service, that each together coordinate in this overall platform functionality. Tenants exist in each of these services, and I've used numbers to identify them as tenant 12, 13, and 14. What's really important here is that the tenant identification not only exists within a service, but across services. So you can track the work that's being done for tenant 12 in the queue service and the worker service. And this allows us to have much more powerful capabilities in expressing how we want to subspecialize based on tenant. For example, you can set configuration settings for these tenants, or you can do things like aggregation of cost across your platform in a first-class way because it's all supported by the service data model. Finally, I want to talk about how the design of ICSP differs because it's being done in a private cloud environment. So you may see similarities with ICSP and other open source technologies in public clouds like Kubernetes or Terraform, and we think these technologies are great and we take a lot of inspiration. However, there are some fundamental differences about what we're optimizing for. In public clouds, you have a large number of customers, and each of these customers may expect different things about how their service layers are run. So that we see that these public clouds need to have a lot of flexibility, but can make fewer hard assumptions about the different pieces of their stack. In comparison, Infra Cloud is basically a private cloud. And what I mean by that is we are both the producers of infrastructure and we consume internally at Meta these offerings. What this means is we can push for much more consistent layers in our stack and have much stronger uniformity assumptions because we are both the provider and the consumer. When you think about things like the domain API, we can actually make sure that all different capabilities implement a consistent interface. And this is much harder when you're in a public environment where you have many different products that may have different interfaces. So we're really excited about the powerful things we can do with ICSP because of this push for uniform behavior. Next, I want to use a couple examples to illustrate how ICSP works. First, let's talk about how a user makes a config change in the system. We have a property in ICSP that human changes go into a central configuration repository and are rolled out to the system. As a user, you can use many different interfaces, though, to author these changes. So you can use our UI console, you can use our CLI, and you can use either your favorite editor or VS Code if you'd like. Regardless of how you create this change, they all end up in a diff to this repository. And because of the consistent format of change, we can have very good expectations as this is validated and rolled out to the system. For example, we always can use the same set of validation and dry run APIs to know what's going to happen as the configuration lands before it does. The second is that all changes can be easily code reviewed and peer reviewed before they go out into the control plane. At the configuration level, I want to talk about what this looks like from a user's perspective as well. So we have a concept called the Service Configuration Graph, or SCG for short. And at a concrete level, these are the config specifications for each domain. In this example, I'm showing you a very simplified version of what autoscaling would look like. It's a YAML file with declarative structure where the user provides the different parameters of how it would like autoscaling to run, such as the step sizes and the resize windows. Again, notice that this is declarative in that the user is expressing to the system what it would like to do, but not how it should go do it. We'd like to focus on the unique parts about this design, and one of the really important aspects is what we call config as data. Because the user wants to provide a structured service to the platform, as we mentioned, there's a topology that they need to subspecialize. We need to make sure that the user can configure these different parts of the topology in a structured and high leverage way. One way you could do this is have the user write scripts and code which sets each piece of this topology themselves. But we found in practice and in large-scale production settings, having code running in line with your configuration system leads to a lot of long-term problems, including how to maintain these systems. Instead, we're trying to make a large bet on having config as data representation, where the user provides a structural representation using concepts like inheritance and patching. To give you a concrete example of how this would work, on the right-hand side, I have a topology that the user would express using the service data model. On the left-hand side, they have the prod section of their service, and on the right-hand side, they have something labeled ASAN, which would be a testing fraction like address sanitizer is a good example where we run a different binary in order to catch bugs. As you might expect, the production side and the ASAN side need to be configured differently. Our configuration system allows them to express this directly in the configuration layer. So here I'm showing that the user can set a specialized setting for autoscaling, the resize window, to 10 for ASAN. And what will happen is that the right half of the service will get this value and its children based on inheritance rules. ICSP's configuration system supports a number of other ways to structure your configuration as well. For example, we support tag groups, which allow more complicated groupings that don't strictly follow this hierarchical tree-like structure. And we also have patch mechanics in case you need to do things like merge, append, or other operations as well. Overall, we're providing a rich configuration system that allows the user to express configuration as data and not as code. The next example I'd like to go over is how multi-tenancy can work in practice and why it's really powerful to be baked into the system as a first-class concept. The example I'd like to use is suppose you're running a database and you want to manage this with many different tenants in the system. Hopefully, folks who have run databases know that you may have different users that want different logical instances of that database, and we would represent these in the system as tenants. Now, because there are large customers and there are smaller customers, you may want the physical deployment of these to be different. Often, large customers need their own isolated deployments, whereas smaller customers can be grouped together in shared deployments that share their resources. ICSP allows you to express this directly to the system. On the left-hand side, we have the shared deployments, and the user can create a structure in their topology which expresses how to physically create shared deployments to things like the deployment subsystem. On the right, we have the isolated deployments. This is where the user wants to ask the system for separate containers per tenant. The really powerful part here is that the user can specify this into the topology and then attach the tenants. So 1 through 4 here are specified to be shared deployments, and then 5 and so on are specified to be isolated deployments. Just by expressing this to the platform will then go mechanically instantiate the right setup for the user. And one of the really nice benefits here is that we're separating out the logical and physical representation for the user. Finally, if you think about something like routing, it's really nice to be able to only interact with the logical layer here. For example, I could say, please route to tenant 4 or tenant 5, and the way I say this is the same regardless of the physical structure. This helps to provide an example of how having multi-tenancy as a first-class concept across all the different capabilities allows you to do really powerful things with more complicated service setups. Finally, we can talk about how AI platforms can layer on top of ICSP to enable new platform applications. So we'd like in the future to be able to use platforms like AI training, serving, or even AI platforms we haven't thought of yet, and give an automation pathway into ICSP to allow these platforms to also actuate the same service management capabilities underneath. As you can see, the layers like the control plane and the capabilities remain the same, even though the actor above them is slightly different, which are these platforms. We think it's much better designed that these layers stay consistent as these platforms are built on than having a separate API standard, and this exposes a lot of the power of the consistency and API-based approach. Let's just take a quick look forward to wrap up. As I mentioned at the beginning of the talk, ICSP plays an important part in the Infra Cloud effort. And Infra Cloud is trying to give access to different infrastructure capabilities to our product developers at Meta. There's lots of products we imagine being in Infra Cloud, such as data processing, storage, AI serving, and training. And as these different applications emerge, our hope is that ICSP acts as the engine to run services underneath each of these. We know that this is going to be a large undertaking, and there's a lot left to do, but we're really excited about the power we've been able to design in ICSP so far, and we're starting to test out these new applications already. Thank you so much for listening to me talk about ICSP and the design.